Good morning, everyone. We're going to go ahead and get started here. Today's webinar is going to be on Basic Hydraulics 1, the movement of the water through the pump. If you were out in Oregon last Saturday, I did part of this for you, because I did the Oregon show out there. But we're going to go ahead and get started on this. It should be about an hour or so at the most. Don't forget that you can always go to thepenteralearningcenter.com, and when you do, you can get pre-recorded webinars, you can get online training, you can also sign up for classroom training here in Delavan if you're interested. All right? So to get started, we're going to go through some what I like to call terms. And these are words or phrases that you may have heard in the past that maybe you understand and maybe you don't. So we're going to go through them now. I want to, first of all, explain that we make centrifugal pumps here at Pentair. That's the primary pump that we make. We do have another division that runs some hog displacement pumps, but what we do here in Delavan is going to be centrifugal type pumps. Centrifugal pumps are called centrifugal pumps because of the fact that they're going to use centrifugal force to move water and create pressure. Now, of course, centrifugal force I learned as a kid because I lived right across the street from the playground, and my buddies and I would go over and we'd play this little game on the merry-go-round. And one of us would get on it, and the rest of us would spin the merry-go-round around just as fast as we could. So the point of the game was you had to try and hold on. Now, I learned very quickly that if I got in the middle of the merry-go-round, I could sit there all day, and those guys would get tired because they'd just be spinning and spinning. Of course, I might get sick and throw up because I don't like things that spin. But if I was out on the very edge of the merry-go-round, then I really had to hold on tight, because the bottom line is the further away from the center that you get of this rotating body, the more force there is, because centrifugal force moves something from the inside to the outside of a rotating body. If you look at the pump there, you're going to notice it has a rotating body on it. All right? Now, the next term that we're going to talk about here is head. In our pump language, head means the energy content of the water. It can be measured a couple different ways. The main way that we use this term is feet of head. Now, it could also be called meters if you're in Europe or someplace else in the world besides the United States. Basically, what you're doing is you're measuring the height of a column of water. That's basically what you're doing here, all right? How high is that column of water? Now, a second way to get that same energy content would be called pressure head. With pressure head, what you're doing, instead of weighing instead of measuring the height of the column of water, you're weighing the column of water in pounds per square inch. So those two things say the exact same thing, but they're just measured a little differently. One measures the height, the other one measures the weight of that column of water. And that's why it's very, very important that we make sure that we understand we're talking about the energy content of the water. What can we do with that column of water? We're going to show you a little more later on. Shut-off head. Shut-off head is a very interesting point on the curve. You can do shut-off head with any pump. It doesn't matter whether it's submersible or above ground. Now, this next picture here shows us the two things that we need to do or have in our system in order to do a shut-off head test. The first is a pressure gauge. On the discharge side of the pump, you want to put a pressure gauge. And then you want to put a valve in. Now, we've used a gate valve, and I know some people don't like gate valves. It doesn't have to be a gate valve. The reason that we've used a gate valve here is because this gate valve has two positions. Fully open, which means we're using the system, or fully closed, which means that we have, we're doing our shut-off head test. Okay? So during the shut-off head test, we're going to take a look here at a couple of things. One of the things that we're going to look at here is the height of the water below pressure gauge. So So we're going to take a measurement. Now you notice in the picture on the right-hand side there says keep it as close as possible. What you're looking for is that vertical distance. That vertical distance. If you look over at the curve, you'll notice that we've got a green line there at zero flow, and that represents that 10 feet of vertical distance from the water to the pressure gauge. All right? The rest of that is going to be the reading on the pressure gauge. So it says 158 feet. So if we've got 158 feet there, and 10 of it belongs to the suction side of the pump, then the other 148 are going to belong to the discharge side of the pump. Now this is very important to remember, because that 158 feet ahead is the maximum head that this can do no matter what. Now what that means is if I've got more friction or more suction, I'm going to get less discharge. There's only so much energy there, and we're measuring both the suction and discharge side. So we want to make sure that we've got an understanding here of what we're talking about. All right? Now, under the word shutoff head, we're going to put the word deadhead here. Deadhead has another meaning, but it's similar to shutoff head. The only real difference between shutoff head and deadhead is you. With shutoff head, you're there. You're the one that turns the pump on, you get the water flowing through the pump, you turn the water off, you take a pressure gauge reading, you measure from the pressure gauge the surface of the water, and then you turn the water back on. Now you can take those readings that you just took, go over to your pump curve and see, is your pump doing what the pump is supposed to do? If it is, then stop messing with the pump, because the pump's not the problem. It's going to be something in your system, okay? If it's not, then we need to look at someplace else. Now, deadhead, on the other hand, is an automatic system that's failed, all right? So let's talk about it here. Oop, I had you raise your hand for something. What is the difference between shutoff head and deadhead? And the difference between shutoff head and deadhead is you, okay? Because with deadhead, what we've got is we've got a pressure gauge, for example, here, or excuse me, a pressure switch, rather, that has failed, all right? Now, a pressure switch has 4 points on one side and 4 points on the other side. Those points are nothing more than a piece of copper that's got silver on them, and the silver part of the points are what touch. Now, the reason that they silver those points that touch is so that the points will open back up. However, if you put too much amperage through there, what winds up happening is the silver melts off and the points weld themselves together. Now, once those points have welded themselves together, well, you know what's going to happen next. The pump's not going to turn off, and you now are in what's called a deadhead application, a pump that needs to turn off but can't, all right? Another area where you may wind up seeing a deadhead application is going to be a timer. If you're doing some sprinkling here, you could have some zones, and basically what you have here is you have the timer that says, okay, let's start the system up. When it says that, it sends a signal to what's called a pump start relay, and the pump start relay closes and sends the juice to the pump to turn the pump on. Now, as it does that, the timer clock also says, let's open zone 1. And so zone 1 opens up, and we sprinkle zone 1, and that takes a half an hour or so. And then what happens? Zone 1 closes and says, okay, now let's open up zone 2. So zone 2 opens up, and we sprinkle zone 2 for half an hour. Then it says, all right, let's close zone 2 and open zone 3, and zone 3 says, no, I don't want to open. You now have a deadhead application, a pump pumping against a closed valve, all right? Deadhead basically means this: something is going to die. It could be the pump, it could be the system, it could be both, but something very bad is going to happen, and that's why we call it deadhead, all right? Now, the next term that we're going to look at here is called, and by the way, if you have a training manual, because you've been to one of my schools in the past, were on the very back cover of that training manual. Atmospheric pressure. Atmospheric pressure basically means nothing more than a barometer reading. That's all that it is. Remember, it's read in inches of mercury. When you read a barometer, it's read in inches of mercury. So because it is, it's telling us how many feet above the water we think we are when we do a barometric, or when we do a vacuum reading on the pump, because it's read in inches of mercury also. So because the atmosphere can be read in inches of mercury, our vacuum reading is read in inches of mercury. Okay? Now, of course, vacuum, that's another thing we have to have. And what vacuum really is something less than atmospheric pressure. Now, we're going to use this to move the water to the pump. So we create a low pressure system, we call it a vacuum, at the eye of the impeller. And then what we do is we allow the atmospheric pressure to push the water into us. So that's how we make our pump work. We'll take a little closer look at that in a few minutes. All right? Cavitation. Now you'll notice the definition of cavitation, because most people, when we come back to the factory school here, within 20 minutes I give you a test. And when you take that test, I got to be honest with you, most people, 90% or so, get that question wrong when I say, what is cavitation? Because they want to believe that cavitation has something to do with air in the pump, but it's not. Cavitation, as you note, says, is the conversion of a liquid to a vapor in a low pressure area. Now remember, we have a low pressure area at the eye of the impeller. If we allow that pressure to drop too low, we're going to wind up with cavitation problems. All right? We're going to convert the liquid to a vapor. All right? Every water, no matter what the temperature of that water is, has a vapor pressure point. And what that means is there is a point at which a water will convert from a liquid to a vapor. Now, this is where I also have to point out the fact that some people think that vaporized water is air, and it's not. It's not. Our atmosphere is actually made up of two things. It's made up of air and water vapor. And how do we know that? Because there's clouds, and it rains on us, and it snows on us, and it won't stop snowing. Oh, I'm complaining, I'm sorry. We got a couple more inches of snow this morning, as a matter of fact. That's because we love snow. So, but it's because that water vapor is up in the atmosphere that we get that snow or that rain. And so it really does point out to us that there is the atmospheric pressure is made up, or excuse me, the atmosphere is made up of two things: vapor, water vapor, and air. Okay? When you lower the pressure over the water, you convert the water from a liquid to a vapor. All right? So right there is where our low pressure system is. All right? We use something called Bernoulli's law to understand that. And basically what he's saying is that because the area between the vanes at the eye of the impeller is so small, the water has to move faster. And when you move out towards the peripheral of the impeller, you're going to find that there's a higher pressure out there. Because of that higher pressure that's out there, we're going to get something called cavitation damage. Now, the cavitation, or the creation of the vapor to a liquid, is not what makes the noise, and it's not what causes the damage. It's when that vapor bubble that we've created gets to a high pressure area, and that high pressure area causes that vapor bubble to collapse. And when it does, you can see holes right through the impeller. Now, of course, that means that this impeller is not going to provide the flow or the head that it used to, because the fact that we have those holes in there. All right? Now, if you look carefully, right there is a vane, and so if you look over at the other paper, or other side there, you'll see there's the vane there, and the cavitation damage happened right on that side of that vane, because that's where there's a high pressure system. So the low pressure system is at the eye of the impeller. There's a higher pressure out towards the peripheral, and as you get closer to that peripheral, that high pressure system will collapse those vapor bubbles. That's what makes the noise. That's what causes the damage. And of course, interestingly enough, the picture on the right, if you look at that carefully, that's a minimum amount of damage. Because if you could get a camera and go on the inside of that vein, you would see that whole area there is pitted on the inside. Now on the outside here we can't see it, but on the inside it would all be pitted. It started on the inside and it worked its way out, so we're actually seeing a minimum amount of damage there. But that whole area would be pitted. Look like someone poured acid on it. Okay? Now, speaking of Bernoulli, Daniel Bernoulli was a scientist who was around in the late 1600s, early 1700s. And he followed in his father's footsteps, who was a scientist, and he came up with something called Bernoulli's law. And one of the things that Bernoulli told us was that a cubic foot of water always took up a cubic foot of space. So what we have here is a 1 foot by 1 foot by 1 foot, which makes that a cubic foot of water. All right? Now, flow rate or capacity deals with the idea of water moving past a certain point in a given amount of time. So what we have here is a square foot. If we want to move that cubic foot of water through that square foot, and we want it to move through there in 1 second, it has to move at a velocity of 1 foot per second. All right? We're going to measure it as it goes past that point, and that's where we come up with our gallons per minute. Remember, we only use gallons per minute here in the United States and the surrounding countries because they buy our pumps from us. Most of the rest of the world is going to use either liters per minute or cubic meters per hour. If I tank that same cubic foot of water, remember Bernoulli said larger area, slower moving water, smaller area, so I put it through a 1/2 foot by a 1/2 foot, now it's going to be 4 feet long. I want it to run through there in 1 second again. Once again, now it's going to move at a velocity of 4 feet per second. So the smaller the area that we take the same amount of water and put it through, the faster the water has to move. That's going to affect your pressure because remember, what we are talking about here is energy. Energy. And so that speed is going to affect your total energy. All right? Now, here's a curve, and the title of the page is Net Positive Suction Head Required. There are 2 types of NPSH. There's NPSH-A, that which is available to us, and there's NPSH-R, that is what is required by the pump. What is required by the pump is built in by the engineer, and there's nothing we can do to change it. We can only change what's available to us. All right? So we need to know what that is. You'll notice the yellow perpendicular line there. That line represents 87 gallons a minute. If you were to go right straight across from where that line crosses the NPSH-R line, we're right at about 18 feet there. Now, most engineers are going to tell you that you can only lift water from 25 feet. So if you can only lift water from 25 feet and my requirement is 18 feet, what does that leave me? And the answer is 7 feet. 7 feet to do what? 7 feet to design the suction side of my pump. Now, it's very important that we understand that 7 feet is going to include 2 things. It's going to include the vertical lift of the pump, so from the surface of the water to the pump vertically, how much is it? And it's also going to include the friction loss through the suction side of the pump. So the friction loss through that piping on the suction side will affect my total vertical lift, which means that's going to affect how much water I can get out of that pump. Now, how does it do that? Well, let's go over here, and we're going to move to the left-hand side of that yellow line, and you can see now we're at 15 feet. That NPSH-R line dropped to 15 feet. Of course, we're only pumping 45, 50 gallons a minute, okay? If we go over to the other side, we're right around 25 feet there. That's the max. And, of course, you can see we're at about 135 gallons a minute there. So, basically, what we're saying is as you change your flow rate, you're going to also change the NPSHR required by the pump. So we can get more water and we can help that water to flow better if we keep the pump vertically closer to the water. But there does come a point where the pump just requires too much, and now you've got to do something different. All right? And that'll be something that we call advanced hydraulics. All right? So, looking at the three states of water, remember Bernoulli told us liquid water, and that's what we're looking at here, liquid water. The molecules of liquid water are so close, so tight, so dense, that as far as we are concerned, liquid water is non-compressible. That was true back in Bernoulli's day, some 300 years ago, and it is still true today. As far as we're concerned, liquid water is non-compressible. Remember, water can turn into a vapor. When water turns into a vapor, basically what happens now is those molecules move farther apart. Remember, they are still water vapor. They did not turn into hydrogen and oxygen. They are water vapor. So they're still water, it's just in a vapor state. And again, that's because we know that because the clouds are up there. Okay? The clouds are where the snow and the rain come from. So with the sun shining, if the temperature is right, it'll pull that right up out of the lake there and up into the atmosphere. Now, of course, there's a couple other types of water vapor. They're a little more, well, let's say, seeable. Okay? For example, steam. If you were to ever watch a pot of water boil, right where the water bubbles or the vapor bubbles are breaking the surface, right there, you'll notice there's nothing there. That's true water vapor. If you go up about an inch or two off the surface of that hot water, though, you'll notice you see steam forming. All right? What that steam really is it's the water vapor condensing, coming back. It's getting too cool, so it can't stay far apart like that, and it's getting too cool and comes back to almost a liquid state. Fog is the same thing when the temperature, the dew point, and the humidity are just right. Fog is going to be pulled up right out of the ground, all right? And as it gets pulled up, again, they don't go real far apart. Far enough apart to become vapor, but not far enough apart to see through, and sometimes fog can get really, really thick. And of course, as you walk through the fog, what happens to you? You get wet, okay? That's because the water vapor condenses back into a liquid on your skin because of the change in temperature. The last type of water over here is called solid water, and with solid water, what basically happens now is those molecules move just a little tiny bit apart. Not far enough to become vapor, but they're far enough apart that ice is going to have a different density, a lighter density, and so therefore it will float on that heavy density water. All right? Now, something else we need to learn about water is it likes equilibrium, and you'll see why here in a second we need to know this. So you'll see on the screen right now we've got two containers. They're the exact same size. If you look down towards the bottom, there's a pipe between them, and there's a valve on that pipe. If I fill one side up with water, when I open the valve, what's going to wind up happening? Water's going to move from one side to the other until both sides have exactly the same amount of water in them. Now, the other thing that we can do is we can offset those containers. Now, it doesn't matter whether you fill the top one or the bottom one. When you open the valve up, the bottom one will have more water in it. But as long as there's enough water there, there's going to be equilibrium. There'll be a level amount of water all the way across there. All right? So once again, why do we need to know this? We need to know this because of where we get our water from. Water is found under the ground. So there's our ground level. Someplace under that ground level, there is a water strata, a water table. Some people call it static water or standing water, an aquifer. Someplace down there, there's water. So what do? We drill a well. We put a casing in that well in most cases, not all the times. If you're drilling a rock well, you're probably not going to put a casing in it. The question comes up, where is the water in the casing going to be? And the bottom line is, in most wells, that casing, or that water is going to be at the same level as the water outside of the casing. All right? And that's simply because of equilibrium. All right? Now, we're going to go ahead and put a screen at the bottom of the well. And the reason we put the screen there is we want to try and keep the large solids out of the well. Then we put a pump in the well. Now, it can be an above-ground pump, it can be a submersible pump, it doesn't really matter. If it's an above-ground pump, we don't put the pump in the well, we put the pump above it, put the suction pipe in. If it's a submersible, well, you can see we put it right down in the well there. The next thing that we're going to do is we're going to turn that pump on. When we do, well drillers call this a cone of depression. Cone of depression. All the way around the well, for so many feet, the water table starts to drop. Now, the water table continues to drop until the water going into the well equals the water going out of the well. When the water going in equals the water going out, we have now reached something called equilibrium. Equilibrium. All right? Water flow in is equal to water flow out. Now, of course, remember that cone of depression meant that the water inside the well has dropped, and of course, installers are going to call that level the drawdown level. The drawdown level of the well. Now, the reason that the drawdown level is so important is simply because of the fact that the drawdown level is the working level of the well. So when you call in and you say, can you help me size a pump? And I say, sure. How deep is it to water? It's nice to know the standing water level. It's imperative that I know the drawdown level. Now, let me give you a little illustration as to why. Let's say that we do a drawdown test in this well. Now, the way they do a drawdown test, a couple different ways. Some of them are going to have like a sonar gun that they have above the well, and they're going to take a reading to the depth of water with the sonar gun. Other guys, one of them, they had a big weight, and on the bottom of that weight there was a concave plate that fit right on the weight, and then there was a line, actually it was a tape measure that was attached to it. They dropped that weight down, and of course as soon as that plate hit that water table, there was a big bang, and they'd stop the thing from falling, and then they'd know how deep it was to water. So they're going to measure the water in the well with the pump turned off and the well fully recovered to the standing water level. Then what they're going to do is they're going to turn that pump on, and they're going to start flowing water out of that well. They're going to determine how much water they're flowing. In this case, let's say they're flowing 20 gallons a minute, and then they're going to continue to take soundings or measurements until the water table stops to drop. When the water table stops dropping, then they're going to say, okay, I did 20 gallons a minute, and it went down 10 feet. So I have a drawdown of 10 feet at 20 gallons a minute. Now, what does it mean to you and me? What it means to you and me is this. When you call up and say, I'm getting 20 gallons at 10 feet of drawdown, and then you tell me, well, I want 40 gallons a minute, it means that your drawdown is going to be 20 feet. And if I don't take that into consideration, you're going to lose about 4.3 pounds of pressure. So this is why that drawdown level is so very, very important, because that is the working level of the well. And we need to make sure that we understand that. Okay? Now, the next slide here talks about centrifugal force. I learned about centrifugal force as a kid. My father actually owned a farm, and so growing up, at least till I was about 5, we were on the farm. Of course, when we came off the farm, my sister got married. You know what she married? A farmer. So I'm back on the farm again. Anyway, I remember when my dad would take a bucket and he'd put some water in it just to show off, and he'd spin the bucket around his head. And of course, as he spun the bucket around his head, what would happen to the water? It'd stay in the bucket. Now, of course, I thought he was a magician. I'm 5 years old, what do I know? So I go ahead and I take the bucket and I start swinging it around. Of course, I'm only 5, so I'm not very strong. And I spin the bucket around. Pretty soon I get tired, and so I stop with the bucket right straight up over my head. And of course, that's when I learned 2 very valuable lessons. It is not magic holding the water in the bucket. It is centrifugal force. And when centrifugal force stops, gravity takes over. So the first thing that happens is you get wet, and then the bucket plunks in the head. Now, of course, if you're smart, that's only going to happen once. Okay? Now, I consider myself pretty smart because I realized, too, that at a young age, that I should never, ever put a hole in the bottom of the bucket. But let's say I did. Let's say I put a hole in the bottom of the bucket, I fill the bucket up with water, and I start spinning it around. What's going to wind up happening to that water in the bucket? It's going to come out. What did I just invent? A sprinkler. Okay? Now, what does this got to do with centrifugal force? The faster that I spin the bucket, 2 things are going to happen. Anybody know what those 2 things are? Water's going to come out faster, and it's going to go farther. That is what we call the first of the affinity laws. The first of the affinity laws. All right? It's very important that we learn this law because what the law basically says is this. Speed is directly related to flow on a 1-to-1 ratio. So if I change my speed by 10%, it doesn't matter whether I go up or down, I will change my flow by 10%. And again, if I went up in speed, I'd get 10% more. If I went down in speed, I'd get 10% less. It's a direct ratio, 1-to-1. This is called the first of the affinity laws. They become more important as we get into advanced hydraulics. Okay? Every pump has to have a driver. So in this picture that you're looking at here, we call this an exploded view. And when you look at this exploded view, you'll notice I've darkened in the driver for this particular pump. And for most of you, that driver will be an electric motor. An electric motor. Okay? Basically what happens with an electric motor, there's 2 parts to it. There is a stator and a rotor. The stator comes from the root word stationary, and the word rotor comes from the meaning to rotate. And so those 2 things put together make up your electric motor. You're going to create a magnetic force with the stator that's going to move around, and as it moves, it's going to pull on that rotor, and that's how that rotor is going to rotate. All right? Now, you could use a PTO. Again, raised on a farm, I know what a PTO is because I used to take the manure out and spread it. And of course, in order to do that, we would load the manure spreader up, we'd take it out, and we'd have it hooked up to the tractor. On the very back of the tractor, there was a stub shaft sticking out, and we would go ahead and we would connect a long coupling to it. So we'd hook up one coupling on the spline shaft of the tractor, and then on the manure spreader, there was another spline shaft. And so we'd hook the other coupling up to that. Then when I would get out into the field, I would stop the tractor, I'd put it in PTO form, and I'd let up on the clutch. And when I did, when I engaged that PTO, that would mean that the spline shaft, the back of the tractor, would start to turn, which would turn the coupling, which would turn the long shaft, that would turn the other coupling, that would turn the gears on that are connected to the shaft on the manure spreader. And that way I could spread manure. With a pump, it's very similar, except instead of using a direct drive, we use belts. And so the PTO runs a belt drive pump, is basically what's going to happen there. SAE stands for Standard of Automotive Engineers. I learned a lot about that when I went up to Fairbanks, Alaska one time. They had a beautiful car museum there, and I learned that way, way back when they first started making engines, they didn't have the holes drilled in the exact same spot every time they made them. And so they'd say, oh, let's put this transmission on here, we'll drill a hole here, we'll drill a hole there. When Henry Ford said, I want to start making an assembly line, that's when they came up with SAE standards, where they said this hole has to be drilled in this place, and it has to be this deep, and it has to have this thread size to it, so that somebody can take that bolt and bolt that transmission to that engine. And basically we do the same thing with a pump. Instead of bolting a transmission, we bolt a pump to it. Now right below SAE standards there, you're going to see a gas engine pump. The difference between the SAE pump and what we call air-cooled engine drive or gas engine pump, that gas engine pump is much smaller. It's designed to pump maybe 50 to, say 150 gallons a minute, so it's not going to have a lot. But of course what happens is the water comes in, the water forces to change, or the impeller forces to change in the direction of the water, and that can really cause a lot of stress. So the bottom line is the difference between the two. There is your this is your SAE dry pump. You'll notice we've got our engine shaft there, we've got a flywheel. On the end of the engine shaft there is a spline. On the end of the pump shaft there's a spline. We have to connect those two together. How do we do it? Well, you'll notice we're going to bring in a spline coupling here, and that coupling is going to actually get bolted to the flywheel. All right? Then on the other side there's another coupling. You'll notice the two don't touch. The two don't touch. So how do we get it to turn if the two don't touch? Between the two of them we're going to do something called vulcanizing, and we vulcanize a rubber to it. Okay? Now those two pieces become one, and we take those and we bolt them in place. Okay? I'm not sure why we're raising our hand here. Why would you use a flywheel coupling versus a hard coupling? Anybody know? What's the purpose of a flywheel coupling? I'm going to take the flywheel coupling and I'm going to put it here. I'm going to bolt it right to the flywheel. When I start the engine shaft turns the flywheel, which turns the plate that's bolted to the flywheel, which is going to pull on the rubber, which is going to pull on the plate that's connected to the pump shaft, and that's going to turn the pump shaft. So the reason that we use a flywheel coupling is because what happens if we get somebody running that engine that doesn't know what he's doing, and he keeps it revved at low RPM? Okay? That's going to cause a lot of torsional vibration. If you get too much torsional vibration, what winds up happening is you get a line that will rip right through that rubber. And what that does is that allows the engine to turn, but stops the pump from turning. By stopping the pump from turning, we are now going to prevent that pump shaft from snapping. Because right at the impeller is where that pump shaft will snap if we get too much torsional vibration. Remember, we're lifting a lot of weight of water, hundreds to thousands of gallons. And of course, like I say, we were changing direction with it, and if we get too much torsional vibration in there, that impeller just snaps right off. So to prevent that from happening, we use a flywheel coupling. Now again, those air-cooled engine drive pumps, because they are smaller, they're not lifting the same amount of water, and so what we're going to do now is we're going to just go ahead and hard couple it. And we're going to just take that hard coupling and mount it right on the engine shaft and let it turn. And we'll drive it direct back. So the next slide here shows us the volute case. I want you to know the volute case looks round. It's not. Okay? There's a hole in the very center of it. We call that the suction or entrance hole. There's a hole off to the side on the top. We call that the exit or discharge hole. What we can't see but is there, and very much implied, is the big hole in the back. You can't see it in this picture, but it's there. We imply it because we've got the gasket there, and if you go back on the motor itself, you'll see we have something called a seal plate adapter, seal plate adapter. Now, the seal plate adapter, if you look at the seal plate portion of it, right where the bolt holes are, you can see there's a little lip that goes all the way around it. Well, there's a lip cut into the volute case too, and basically what we do is we put that gasket on there and then squeeze those two lips together and bolt them, and now you're not going to get water out of there. That's why we don't talk about that hole, because we really don't use it very often. It is called a back-out style pump that we make here. It's called a back-out style pump. All right? Now, of course, what makes it back out, you take the bolts out of the seal plate from the volute case, and now you can go ahead and separate that pump. You can leave the volute case hooked up to the piping system as long as you know that you don't need to take it out. All right? The next thing we want to talk about there is you'll see those bolts that are going from the adapter into the motor. All right? Again, the purpose for that, we do not want the seal plate to move. We want that to be stationary. We don't want the volute case to move. We want that to be stationary. So by bolting the adapter seal plate to the motor, stator, stationary portion, none of that's going to turn. Now again, those bolt holes have to be in a certain spot. Only now, because it's an electric motor instead of a diesel engine, this is called a NEMA standard. NEMA is NEMA, and it stands for National Electric Manufacturers Association. So that's what we're looking at here, the National Electric Manufacturers Association. They tell manufacturers of electric motors where they need to drill that hole, how deep the hole has to be, what thread is in there, so that we as a user of their motor can purchase that motor and know where we have to drill that hole in the adapter and what size bolt we have to buy so we can get everything tight the way we want it. The other thing the NEMA standard means is it tells us how far that shaft is going to stick out of that motor and whether it is a keyed shaft or a threaded shaft. So that's what our NEMA standard means for us. All right? So those are your seal plate adapter and the volute case. The next slide here that we're going to look at, there's your impeller. Your impeller. Now, the impeller is the part of the pump that does the work. And you will notice when you look at the impeller that there's a hole in the very center in the middle of it. That hole is going to fit into the suction hole. That hole is called the eye of the impeller. The eye of the impeller. You can see that there are some vanes. If you look at the outside edge, you can see some vanes. And of course, covering those vanes is something called a front shroud. Now, the reason they call it a front shroud is simply because of the fact that the suction of the pump is generally considered to be the front of the pump. So that blue area there, that's called the front shroud. If you look at the gray area, that makes up what's called the back shroud, because most people consider the motor to be the back of the pump. All right? And so what that means is, because we've enclosed the vanes on both sides, this is called an enclosed or closed impeller. By enclosing those vanes, we force the water in through the eye and out through what is called the port. Now, it's very, very important. Remember, we just said a few minutes ago that the speed of the water determines the flow and head that I'm going to get out of that water. Well, what else determines the flow? The maximum flow is determined by the port width. So the wider that port width is, the more water I'm going to get through there. Now, the next slide here gives us a little closer look at that impeller. Remember, there's the impeller eye. That's where the water's going to go in. Then you've got the impeller vane. As the water goes into the eye, the impeller vane is going to pick it up and push it. Now, I want you to understand, there are two views here. All right, if you look at the view on the right, you're looking at the front of the impeller. If you look at the view on the left, you can see the back of the impeller. All right, the reason this is important in the fact that we've covered that vane is because by putting those shrouds on that vane, it cuts the water and moves it. Now, of course, the impeller is going to turn. By the way, if you haven't figured it out yet, the impeller is the bucket with the hole in it. Okay? So the impeller is going to turn, and it's going to rotate. The question is, which way does it rotate? Does it rotate clockwise or counterclockwise? And that all depends. Are you looking at the eye of the impeller, or are you looking at the hub, which is in the back of the impeller? All right? If you're looking at the eye of the impeller is going to turn in a counterclockwise direction. If you're looking at the hub, most electricians are going to tell you that the impeller is spinning clockwise. So it all depends on your orientation. Now, again, the reason that's important is because you'll notice that this is a water slinging device. So as the water gets pulled into the eye and gets pushed out through the vein there, that the vein is going to increase the velocity of the water. That's the whole purpose of that vein. All right? The impeller passage is the area between the vein, and again, if you look at the eye, you'll see that that area is much smaller than if you look at the peripheral. So, of course, you're going to have faster moving water at the eye, which means you're going to have a lower pressure than you are out at the peripheral. The impeller port, remember the impeller port is the width of that vein, is the spacing between the shrouds, and that's going to determine the maximum flow of this impeller. There comes a point where the friction loss through the impeller gets so great you cannot get any more water through that impeller. All right? And then the last thing there is the impeller peripheral. That's the outside edge. That's where we've added the maximum velocity. Once that water comes off that peripheral, we can't add any more velocity to it. Remember, we're going to convert energy here. All right? The hub, remember, the hub is that very last point there on the back side. That's going to hook up to the motor shaft, and that's what's going to turn this impeller. So that motor speed is part of what determines the complete velocity of the water as it comes off of the impeller. What speed am I turning that hub at? All right? So speaking of that, synchronous electricity has 60 hertz. 60 hertz means 60 cycles a second. 60 cycles a second means that we're going to have 3,600 cycles a minute. Now, another way of saying that would be revolutions per minute. With the induction type motors we use, however, by the way, AC electric was invented by a guy named Nikola Tesla. So was the induction motor that we use. And Tesla realized that doing single phase, if you didn't make this thing turn, it wouldn't. It would just bounce back and forth. So if you've ever had a motor that just hummed, that means that our starting mechanism didn't work properly. And the shaft, instead of spinning, is just bouncing back and forth between a north and south pole. All right? So to get it spinning, we have to do something called slip. We build slip into the motor. By building slip into the motor, what basically happens is we're going to spin that hub at 3,450 RPMs. Now, of course, here comes a trick question. What's the RPMs out here in the peripheral? And the answer is the same. The amount of time that it takes to go around there is the exact same amount of time that it takes to go around there. The difference is if you take that hub and stretch it out as a straight line, I'll look up at the top of the screen there, okay? And then you take that peripheral and stretch it out as a straight line. Now remember what we're doing. We're trying to increase the velocity of the water. So we're going to move the water from that point to that point in the exact same amount of time that we move the water from the same point over to this point. So what has to happen? The water has to move faster. So what we've just learned is while RPMs are one way to add or subtract speed to the water, so is the diameter of the impeller. If I make a larger diameter impeller, I get more speed. If I get more speed, I get more flow. Are there any questions about this? So remember, flow is directly related to speed on a 1-to-1 ratio. We're going to use RPMs from the motor and impeller diameter to create that speed. Okay? Now, again, this is just to point out that the water is going to get pulled in. Remember, this is turning in a counterclockwise direction. So you see where it says high pressure there, that's where the water is going to move along the vein. And of course, you can see as we move from the eye of the impeller to the peripheral of the impeller, that area increases in size, and as it increases in size, it is also going to wind up increasing in pressure. So even though we are increasing the velocity of the water, we are also increasing the pressure of the water because we're giving that water more area to move through. That becomes very important when we get into our advanced hydraulic classes. Okay? So there's the area at the eye, and there's the area at the peripheral, and you can see there's much more area at the peripheral. So according to Bernoulli, because we've got more area, we'll have higher pressure. Okay? It's not too unlike when I take a paddle, say I've got a canoe or a kayak, and I'm out in the lake. I take the paddle and I put the paddle down in the water and I pull. As I pull, one side is going to have a high pressure area, the other side is going to have a low pressure area. The difference between the impeller and the paddle, I'm going to take the paddle out, and when I do, those two will come back together. With my impeller, I'm hoping I've got an endless supply of water, and that high pressure is going to continue to move the water into my system where I want it. The low pressure will continue to encourage the high pressure to move in that direction. All right? So, we're talking about energy here. We're talking about increasing the speed of the water. There is a formula, it's in the advanced hydraulic courses, that talks about how velocity can become energy. So you'll notice in our picture here, we do have velocity energy. The impeller is round. We know it's round. It has to be round. If the impeller is not round, what's going to wind up happening? We're going to ruin the bearings because that impeller is going to bounce all over on the end of that shaft. So that impeller has to be round. We have to make them that way. I told you earlier the Volute case looks round, but it really isn't. And now I'm going to prove it to you. How so? I've got something called the cut water there. All right? If you look at where the cut water comes closest to the impeller there, all right? Now, of course, the reason we call it the cut water is we want the water at that point to go out through the discharge rather than follow back through around. So that's why we call it the cut water, because we want to cut it and have it go out. But notice the area right here between the impeller and the Volute case. And then as we go around, you'll notice that, and again, we're going in a counterclockwise direction, the area between the impeller and the Volute case keeps getting larger and larger. There is a reason for it. The reason simply is this. We're collecting that water, we're going to slow the velocity energy down, and we're going to convert velocity energy to pressure energy. Now, I want you to understand, any pump company, including ours, can only add so much velocity to the water. So the bottom line is, when that water comes out of that discharge, what you do is going to determine what's going to happen next. If you come out of there with smaller pipe, yes, I've seen people do that. What's going to wind up happening? You're going to immediately force that water from a larger area into a smaller area, which means you're going to increase the velocity, and as you do so, that's going to decrease the pressure. If you use the exact same size pipe, well, we've added all the energy we can, we're going to start decreasing in energy. If you put a bigger pipe on that discharge side, as that water comes out of that discharge, it's now moving into a larger area. It will continue to slow down for a while, which means it will continue to increase the velocity or the pressure energy. So it's your choice what you want to do, all right? I want to make sure that you understand it's totally your choice. I also want you to understand that the discharge pipe should never be larger than the suction pipe. So if you're going to put a bigger discharge pipe on there, you probably should put a bigger suction pipe on too. There's a class coming up here shortly that's going to show you how many pipe sizes you can go that's reasonable. All right? So everybody understand that? Any questions about it? Very, very important that you understand at the discharge, we've added all the energy we can. What happens out of that discharge to that energy is totally up to you. All right? Submersible pumps, and again, pump companies all make submersible. It doesn't matter whose you're purchasing. The bottom line is a submersible pump is a submersible pump. All right? They're all going to have an impeller in there. And if you look at this impeller, this is our impeller, you'll notice that we're looking at the top of the impeller. The bottom of the impeller is where the eye of the impeller is, where the water is going to go in. The top of the impeller is where the water is going to come out of. It's very important that you know, right here, the bottom shroud, where this suction hole is, the bottom shroud is complete out to the edge of the vane. So it's completely round, all right? Every pump company is going to open that top shroud up a little bit. You can see how we do it here. It almost looks like there's a teardrop in the top shroud at each of those veins. I'm going to tell you right now that all pump companies do that. Either they put the teardrop in there, or they're going to cut the vein back a little bit, or I mean the top shroud back a little bit so the vein sticks out. The reason that we want the vein to stick out is so that when the water comes through the impeller and it comes out of that vein, because it's got something on the bottom and nothing on the top, it's going to have a upward direction, which is what we want it to do. We want it to move upward. And that's the purpose of shrinking that top shroud a little bit. Okay? Every pump company is going to have at least 3 parts here. We have 4, but the other pump companies are all going to have 3. All right? The bottom part there is called the plate. That little part coming up from there is the part that we add. That's called a thrust pad. Everybody's going to have an impeller. Most impellers are going to have 5 or 6 veins in them. And then they're going to go up to the diffuser, and the diffuser has 5 veins in it, 5 channels. Okay? Again, the purpose of the parts. The plate at the bottom, that spacer at the bottom, is to force the water into the eye of the impeller. Remember, that spacer is going to sit on top of the diffuser, and so that's how you build what we call a stack. That's how you build the stack, okay? And so then what happens is the water goes into the eye of the impeller. It comes out with more velocity. That velocity is captured through the holes that are in the bottom of the diffuser. Now, it's nice and smooth in the bottom. On the top, there's channels, and of course, that water is going to come out of there with velocity and go up through those channels. As it moves through those channels widen as they move towards the inside, which means the water is going to slow down, and we're going to convert the velocity energy into pressure energy. All right? A submersible pump is nothing more than a centrifugal pump. It's just that because of the size of the pump, we have to include stages. The first pump, the one on the bottom, determines the flow. Every pump after that just adds head. And that's because we can't make that diameter any larger. So we have to add more impellers to get more head out of it. Okay? A stage is made up of an impeller, a diffuser, a plate or spacer, and a thrust pad. So don't forget, we throw the thrust pad in there. That's something specific to our pump. All right? You'll notice on the picture of the diffuser that it shows that round ring off to the side there. That is a ceramic seal, and that thrust pad seals the hole. You've got a hexagonal shaft which means it can't touch that round hole in that ceramic seal, and so the thrust pad seals that. Other pump companies do it other ways, but that's how we do it. All right? So there's your impeller, there's your diffuser. They have to work together. Remember, one's going to increase the velocity, the other's going to decrease the velocity. There's your plate down here, and that plate is what's going to force the water into the eye of the next impeller. And there's your thrust pad. All right? Remember, horsepower is determined by the number of stages. So I lift so much water, the reason I put horsepower on here is so I can lift it higher. Any questions? All right. Diffuser is used in a self-priming pump. So far we've talked about a straight centrifugal, we have talked about a submersible pump, and now we're going to talk about self-priming pumps. The impeller is going to run on the inside of the diffuser. Okay, it's just like that straight centrifugal pump, except that the pump body is so much bigger. All right, and because the pump body is bigger, we've got to control that water, so we use the diffuser. So the impeller fits on the inside of the diffuser, and obviously the impeller eye is going to go through that hole in the middle there. That's where a wear ring is. And then you'll notice there's all those channels on the outside. If you look at where the channel is closest to the impeller, and then look at where the channel is furthest away, you can guess right away what that channel is doing. It is slowing the water down and converting the velocity energy into pressure energy. All right? Now, to show you how the other side of the diffuser works, we're actually going to build a pump. So this is a seal plate. You can see in the middle of the seal plate there's a borehole, and in the middle of the borehole there is a hole drilled right through it. The middle of that borehole is there so that way we can put the pump shaft through it. Now, once again, it's very important to remember that the pump shaft cannot be the same size as that hole. If it is, they will spin well together. Can't have that. So because we can't have that, we make that hole a little bit bigger. However, we have to plug that hole, otherwise the water will go out of the hole. So we use something called a mechanical seal. It's got two parts. It's got a stationary portion, and it has a movable portion. Now, if we take a closer look at real seals, there's two real seals here. There's the stationary portion. You'll notice that the surface of the stationary portion that's facing the rotating seal, the rotating part of the seal, that's going to be a very highly polished ceramic. You don't want to touch that because the oils on your skin will get on that ceramic and that will shorten the life of it. Where the arrow is pointing, that is a rubber boot. The rubber boot goes up the side and under the bottom of it. And that rubber boot is what's going to stop the water from going through the outside of that borehole. All right? Now you'll notice on the rotating part, there is also a rubber boot. Now, there's two different types of seals you're going to use. The one on the bottom and the one on the top. They're really the same, but they're different. What's different about them, you'll notice the one on the top has the rotating seat with the spring in it. The spring is part of that rotating seat. Okay? Here the spring is separate. It's going to go on the rotating seat. The purpose of the spring is to keep compression between the carbon piece that's on the bottom of the rotating seat, and that carbon piece faces the ceramic, and those two pieces are going to turn. They're going to get very, very hot, so you've got to have water going between them to cool them off. All right? You'll notice, too, that there is a rubber piece inside of that rotating seat, and you're going to need to put, on both of those rubber pieces where the arrows are pointing, you're going to need to put a lubricant. All right? I've seen guys just spit in their fingers and use it. I've seen guys use dish soap. You need to make sure that the lubricant you're using is not a oil-based lubricant. An oil-based lubricant will destroy the rubber, so you need to have a water-based lubricant. I know that it sounds funny, but I like to tell people to use KY jelly, because KY jelly is a water lubricant, and you can use it very easily on here. It works very well. You need the lubricant on the stationary seat because you're going to seat that stationary seat over the shaft into that borehole, and the rubber's a little bit bigger, so you want to make sure it slides in easy. Now, when you go to slide it in, remember you're not supposed to touch that front surface there. So if you don't have a cardboard O-ring that comes with it that goes over the top, so you can just push it down, either use latex gloves or use clean paper. And when I say clean paper, I'm talking about paper towel, all right? And then on the rotating part of the seal, you're going to put just a drop on the inside there because, again, remember, that rubber is so tight on that shaft that it will turn with the shaft. If you use that KY jelly, you put it on there, just insert a little bit, just a little drop on the inside, and then go ahead, use your thumbs to push on the rubber so the rubber doesn't pop out. And that'll allow that rubber to slide over the shaft very easily, but trust me, when it comes time, it will turn on. Now, when you come back here to the factory and we take the pump apart, I always tell you when you go to put the pump back together that you need to take a 7/16 wrench on the control end of the motor to hold the shaft in place so that you can take the impeller off. However, when you go to put the impeller back on, now you can go ahead and take that wrench off. When the impeller gets tight enough that the shaft starts to spin, you've got enough on there to close that area up. The only time that I can say that there's going to be a problem is if you're not getting the pump to prime, then you may have to tighten that shaft a little bit more. But I don't recommend it unless you absolutely have to, because every time that pump turns on, that impeller, when it spins, is going to tighten that shaft. And as it tightens that shaft, it's going to create the correct amount of pressure or tension on that spring. Okay? Then we're going to put the diffuser over that. We're going to put a diffuser ring over the end of the diffuser. Now, it's very important that we understand this.
Put the gasket in place, then we're going to bring the pump body over it. When we tighten the screws and pull that pump body up tight against the gasket and seal plate, you'll notice also in the middle there's a hole, and that hole is going to be tightened right around that diffuser ring, so we form a nice tight seal there.
When the diffuser ring compresses, that forms two different chambers. You've got a suction chamber and a discharge chamber. And of course, we're going to create a low pressure at the eye of the impeller, which is going to push the water in. And then, of course, the high pressure on the other side is going to push the water out. The thing you have to be concerned about is this, all right? We are creating a low pressure here. Sometimes if we pull sand, silt, or grit into the pump, that area between the impeller eye and the wear ring of the diffuser needs to be lubricated. So we're going to pull water. Remember, we got high pressure water there at the discharge, so we're going to push water through this way, and it just recirculates. All right? If you get too much sand or silt in there, what winds up happening is you wind up widening that area out. That area is only 75/10,000ths of an inch. If you widen it out too far, you get more water going through there than you do out the discharge, and your customer's going to complain, I'm not getting the pressure I used to get. So when they say that, that's one area you have to check. The other area you have to check is going to be in that diffuser ring. One of the reasons why people like to get above ground pumps is because they get to fool with it before they call you. And so if they don't put that diffuser ring in, or if they cut it when they put it in, what winds up happening, right there's your diffuser ring, you're going to get water to recirculate that way. So those are the two areas you want to look when people say, I'm not getting the same flow or head that I used to. All right, I've got some questions for you. Please take your phones off of mute so you can answer these questions. All right, first question, what does head mean to you? It should mean the energy content of the water. All right? Head is the energy content of the water. Remember, it can be measured one of two ways, vertically by feet, or you can measure the weight in pounds per square inch. Second question, what two things make up shutoff head? The shutoff head is made up of the suction side of the pump and the discharge side of the pump. Remember, as one changes, the other one's going to change. Thank you so much for being here. I really appreciate it, and we'll look forward to seeing you this afternoon.